Assalamu alaikum and welcome to this fascinating journey into the world of astronomical calculations for prayer times. This is the first episode from a series of episodes exploring the subject in details. The beautiful thing is not only that we will know the equations and formulas that we will use to calculate them, but the fact that we will know why they work. Each episode in this series will have two versions, one in Arabic and one in English. This English version will have captions in English, and you can use YouTube translation feature to choose translation of captions to tens of languages supported by YouTube. This episode will cover conversions of units in astronomy calculations. It will explain the effect of atmospheric refraction on observations, and will also explore how an observer height can change the results of calculations. Let's begin. Let's start with a common task, converting coordinates. Location coordinates like longitude and latitude are sometimes given in degrees, minutes, and seconds. For example, Mecca is at latitude 21 degrees, 25 minutes, and 21 seconds. So these are the degrees, the minutes, and the seconds. And the coordinate here is given in three numbers. But in astronomical calculations, we need one number to represent the degree and fraction of a degree. And Mecca latitude in this format is 21.4225 degrees. But how do we convert between the two? To convert from this to this, we'll say latitude equals degrees plus minutes over 60 plus seconds over 3600. Because a minute is 1/60th of a degree and a second is 1 over 3600 of a degree. To convert from this to that, degrees is the integer part, 21. Minutes, we subtract the integer and multiply the remainder by 60, and then take the integer. We subtract the integer again, multiply the remainder by 60 again, and the result is the seconds. Let's do this in Excel, which we will use for calculating prayer times. If these are degrees, here are minutes, and here are seconds. And we use the coordinates of Mecca to 21 degrees, 25 minutes, and 21 seconds. We now calculate the latitude, which is degrees plus minutes over 60 plus seconds divided by 3600. For the reverse conversion, if this is latitude, we use the same latitude for Mecca. Here are the degrees, minutes, and seconds. So degrees is the integer of latitude. Minutes is the integer of latitude minus degrees, all multiplied by 60. And seconds is latitude minus degrees minus minutes over 60, all multiplied by 60. But there are two important notes here. The first is related to rounding. For example, if we write the number 1 degree and 20 minutes and 0 seconds, we see the result as 1.33333. If we take the same result and convert it again, we notice the odd number in the seconds, minus 2 times 10 to the negative 13th power. If we change the degrees to 2, this should only change the integer part, but we notice that the seconds change. If we put 125 degrees, we see 19 minutes and 60 seconds. But we know that minutes and seconds do not equal 60 because 60 seconds is 1 minute. But this is all caused by rounding in Excel. There is an easy way to solve this problem. When we add a small number to the minutes, something like 10 to the power minus 8, and we round the seconds to the nearest second, or 1 decimal place, or 2 decimal places. For information, if we are measuring distances on Earth, the difference between one arc second and the next is about 30 meters. If we want more precision, we can add 1 or 2 decimal places. But even if we are not using seconds at all, the difference between one arc minute and the next is less than 2 kilometers, or 1.3 miles. If we use degrees and portions of degrees, and we use only 2 decimal places, the difference is approximately 1 kilometer. If we add a third digit, the difference will be about 100 meters. The fourth digit will make the difference 10 meters. We can add any number of digits, but when we are calculating prayer times, we usually calculate prayer times for cities that are kilometers apart, and high accuracy is not required. The second issue is about negative numbers. If the longitude is west of Greenwich or the latitude is south of the equator, the number will be negative. If we go back to the latitude of Mecca and assume we use the same numbers but in negative numbers, the conversion will be incorrect. The solution is not to use negative numbers until we complete the conversion, then we will add the negative numbers. The same conversion method can also be used to convert time. Usually we represent time as hours, minutes, and seconds. And when we use this conversion, this will give us the hours and fractions of an hour. However, in astronomical calculations, hours are considered fractions of a day, meaning if we put the number 1.5, that does not mean an hour and a half, but a day and a half, a day and 12 hours. To convert hours to fractions of a day, we divide by 24, because a day is 24 hours. And this is how Excel stores time. If we take the same value and use the time format, we'll see that the time is displayed. The next conversion we'll do is degrees to time. In astronomical calculations, time and angles are closely related. The Earth rotates 360 degrees in 24 hours, which is 15 degrees per hour and 4 minutes per degree. For example, the longitude of Mecca is 39.8262 degrees east of Greenwich. To calculate the time difference in minutes between the sun passage over the meridian in Mecca and Greenwich, multiply the longitude by 4, which equals 159.3 minutes. If we want to calculate the difference in hours, we divide it by 15, which is equal to 2.655 hours. To convert time to fractions of a day, we can divide the number of hours by 24, or divide the minutes by 1440, which is the number of minutes in a day, or divide the angle by 360. And all of these will give us the same result. If we use the time format, we'll see that the result is 2 hours, 39 minutes, and 18 seconds. We can also convert time to degrees. For example, if the hour angle or HA of the sun is 4 hours, 50 minutes, and 15 seconds, we can convert it to degrees. First, we convert this to actual hours, and the result is 4.8375. To convert this to degrees, we multiply the hours by 15, giving us 72.5625 degrees. The third transformation involves measuring angles. As we know, angles can be measured in both degrees and radians. This is important because many equations in celestial mechanics we use trigonometric functions such as sine or cosine or tan, and some programs, including Excel, use radians to measure angles and not degrees. Therefore, before using these trigonometric functions, we need to convert angles from degrees to radians and vice versa. To convert from degrees to radians, we multiply by pi and divide by 180. And to convert from radians to degrees, we multiply by 180 and divide by pi. Excel has a function called radians to convert degrees to radians, and another function called degrees to convert radians to degrees. We can also define a cell in Excel named degree and assign it the value 180 over pi, and we can name it DEG. And another cell named rad and assign it the value pi over 180 and name it RAD. To convert degrees to radians, we multiply by rad, and to convert from radians to degrees, we multiply by DEG. Now we covered most of the conversions required for our calculations. The second part of this episode is the effect of refraction on calculations. When we observe objects in the sky, Earth's atmosphere bends the light, making them appear higher than they actually are. This is called atmospheric refraction. This is why the sun appears slightly above the horizon, even when it has already set. And there are multiple formulas to calculate the atmospheric refraction. One of the most widely used equations is cot, which is the inverse of tan, of E plus 7.31 over E plus 4.4. And E is the altitude angle of the object in the sky above the horizon measured in degrees. The result of this equation is in arc minutes, so we need to divide by 60 to convert to degrees. If we plot the refraction angle versus the altitude, we notice the relationship between the refraction and the altitude of the objects above the horizon. The effect is strongest near the horizon, where objects appear very close to the horizon with a value of 0.5746. And as the altitude increases, the refraction decreases. So when the altitude is 20 degrees, the refraction is 0.045, which is almost 10 arc seconds. Refraction also depends on temperature and pressure. These values assume the temperature to be 10 degrees Celsius and the atmospheric pressure is 10 millibar. If the temperature or pressure is different, we can correct the refraction by multiplying by P over 1010 multiplied by 283 over 273 plus T, where P is the pressure in millibar and T is the temperature in Celsius. In our calculation, we will assume the value of 0.5634 when the object is at the horizon, meaning it's either rising or setting. And because we will use the sun for prayer times, we need to add half of the sun apparent diameter. The sun mean apparent diameter is about half of a degree, which is 0.5332 to be exact. If we divide this by 2 and add it to the refraction angle, the total refraction effect that we will use is 0.8309. If you want to be more precise, you can use different values for temperature and pressure, and you can also use the more precise sun apparent diameter that we will also calculate. The third and last part of this episode is the effect of the observer height on calculations. The higher the observer, the earlier the sun rises and the later the sun sets. But first, let's know what we mean by height. Height here does not mean the elevation of the observer above sea mean level. Height refers to the difference in elevation between the observer and the ground around him, say 5 or 10 kilometers. For example, if the observer is in a plateau that's equal in height, then there is no effect regardless of the elevation of the plateau above sea level. Well, there is, but we can ignore it. However, if the observer is here and this is the direction of east and this is west, then this height will affect the sunrise, but because the west side is level, there will be no effect on sunset. And if the observer is in top of a mountain or a skyscraper, then both the sunset and sunrise will be affected. The effect of height on sunrise and sunset can be calculated using the formula inverse cosine of 6371000, which is the Earth radius in meters, divided by 6371000 plus h, where h is the height of the observer in meters. If the observer height is 100 meters, for example, the angle is 0.321 degrees, and this angle can be added to the refraction angle to take the height into account. If the observer lives in a skyscraper 400 meters above the ground level, sunrise will take place 2.6 minutes earlier and sunset will take place 2.6 minutes later. From an airplane 36,000 feet high, sunrise will happen 13.5 minutes earlier and sunset will be 13.5 minutes later. In summary, in this episode we have explored essential astronomical calculations from unit conversions to the effects of atmospheric refraction and the effects of height. Starting from next episode, we'll start the actual calculations of prayer times. Wish you find this episode useful. Please subscribe, share, and enable notifications. Thank you very much. Until next episode, keep safe.